Okay, section 8, pressure sensors. As with potentiometers, and I'm not sure I made this clear, the first sensor that was in there was the throttle position sensor, and we really focused on that. But we also said that a potentiometer is a potentiometer, and the testing methods are going to be the same across the board. So it doesn't matter where it lives, what kind of car it's in, what year, make, or model, testing of that potentiometer would be identical across the board, including other components that maybe are not automotive related. A potentiometer is tested the same way. The same thing happens with pressure sensors. Our focus I have in here is the MAP sensor. Of course, we're talking about engine performance diagnostics, so the MAP sensor would be the main pressure sensor. But I want you guys to know that all of the information in this chapter, in section 8, is going to be universal. Even though we're talking about the MAP primarily, and all the testing methods are for the MAP, these same methods can be used across the board. It can be a fuel tank pressure sensor, which they use for evap systems. It can be AC pressure sensors, where they monitor low and high sides of an AC system. It can be barometric pressure sensors that have separate BARO sensors on cars. Of course, the MAP itself. Fuel pressure sensors, some of our electronic returnless fuel systems will use a pressure sensor on the rail, and you can actually monitor fuel pressure with the scan tool. Kind of nice system for that reason. But testing of these, detailed testing of a pressure sensor, is going to be identical across the board, just like the potentiometers was. Okay, so we're going to jump into this, starting with the MAP sensor, which is on page 2. And our MAP sensor on a non-mass airflow engine, a MAP sensor is the critical player. Of all the sensors we've talked about so far, engine coolant temp sensors and intake air temp sensors and throttle position sensors and oxygen sensors, this MAP sensor has the most effect on what kind of fuel delivery you're going to have at pretty much all points in time. You remember the coolant sensor? We said the coolant sensor was a warm-up type sensor, and it was really critical for starting and warm-up period. But once the engine warmed up all the way, it really took a back seat. I mean, it was certainly used for cooling fan control, but from that point, it really wasn't a big factor on driving down the road and varying loads and speeds. That coolant sensor really wasn't in play that much anymore. The throttle position sensor is a pretty critical sensor, but in comparison to the MAP sensor has way more weight in it than a TPS will. An example that I have for you is actually here on page 4. Let's just jump down to that real quick. And what I'm showing in comparison of the two sensors, I'm showing you a throttle position sensor compared to a MAP sensor. And here's what I did. I took a vehicle and I measured the injector pulse width at idle, and I measured the injector pulse width in gear. And basically what I did is I changed the engine load, but my focus in here was keeping the same throttle angle to show you that throttle angle and engine load don't always go hand in hand. Basically, so what I'm showing you in this picture is the TPS is not the one that's a factor in this pulse width change that you're looking at on the screen. So the red channel, which is my throttle position sensor, B, channel B, this red trace is showing you about a half a volt in both pictures. So we have the same throttle angle in both pictures. And then what we're looking at, the green trace, is our injector current ramp pattern. We talked a little bit about current ramping, and where I'm connected would simply be on either the feed or the control for the fuel injector. This is your injector. I'm using an amp probe either on the control or the feed wire. Either side will show me current flow, and I'm looking at the on and the off time of that fuel injector. And so the beginning of the ramp would be, this is your on time, that's where it starts, and right there is where it shuts off. And the distance between the cursors would be your injector pulse width in this picture. So you look at the bottom picture, we have a pulse width of 2.95 milliseconds. We look at the top picture, we have a pulse width of 4.54. Same throttle angle. What changed? Engine load changed. Which sensor is the one that's sensing this engine load? Is this MAP sensor. So I'm at 1.1 volts on the MAP down here, 1.6 volts up here. How much does this MAP sensor show engine load? And in this picture, it's pretty clear. I'm at 3 grand down here, and I'm at 1100 up here. And why it's like that, same throttle angle. How can you be at the same throttle angle at 3,000 RPM and at 1,100 RPM? And the answer is engine load. I'm doing a brake torque in the one picture, and I'm doing a freewheel spin in the other. By freewheel, I mean it's in park, no loads, a dead rev it's called. So think about it like this. We've all sat in our cars and given it a little bit of gas in park, winter time. How much throttle angle does it take to raise your RPM when you're not in gear? Not much at all, right? And that's the point. In this picture, throttle angle, RPM, they don't really go hand in hand, do they? Look, I got same throttle angle, 1,100 RPM and 3,000 RPM. So this picture does two things. One, it shows you the limitations of the TPS, doesn't it? In both pictures, I have the same throttle angle. So does it show you the need for another sensor? More than just the throttle position sensor. We need another sensor that's telling the engine load. So back up to the map. Our map sensors indicate engine load. Engine load and engine vacuum go hand in hand. You guys ever seen the aftermarket fuel economy gauges you can put in your car? They have a vacuum line going to them. What it's doing is you're just monitoring engine vacuum. And if you can drive your car with the highest amount of engine vacuum, you're going to get the best economy. Engine vacuum and engine load go hand in hand. Think about engine vacuum as the absence of atmospheric pressure. And the more atmospheric pressure we have in the intake, the more that engine's breathing and the more fuel we need. So it measures manifold pressure. And I'm showing you pressure and vacuum are opposite. High pressure is low vacuum. So high pressure would be a heavy load. Computer's going to add more fuel. Low pressure is going to be a light load. We're going to get less fuel. So you can think of it as you want. You can think of it as pressure. You can think of it as vacuum. But that's what this sensor's doing. Over here, we got a title or a name that you guys need to learn. It's called a speed density system. A MAP sensor is the primary input for engine load on a speed density system. There are two types of systems. We talked about this in section 1. I don't know if you guys remember when we talked about vacuum leak testing on a MAP and a mass airflow engine. And if you remember, I used this term, speed density, before. What is it? It is a mathematical calculation to determine incoming airflow. You want to remember this title, this name, speed density. You'll hear it a lot in this field. Here's another way you can look at it. A speed density engine, there is no MAP. There is no mass airflow sensor on speed density engine. We had a 2005 Chevy Trailblazer in here last week. You guys were concerned about running that engine with the air intake tube off, and I told you not to worry about it because it is a non-mass airflow engine and it won't affect it. The technical term for that would be that was a speed density engine. So no mass airflow. And its title, that name, is just a mathematical formula. And they use some factors in there. Throttle angle, air temperature, old terminology here, CTS would be coolant temp sensor. Today's OBD2, they mandated terms too, and the term or abbreviation would be ECT, engine coolant temperature, but you know, CTS was an older term used by GM and some other manufacturers. Engine speed, which would be cam and crank, of course, is important. Volumetric efficiency, how much that engine breathes. Cam design, number of valves per cylinder, bore and stroke, turbo, non-turbo, and then of course some EGR gases that are going to dilute the airflow in that cylinder, right? If we dump EGR gases into a cylinder, you're not going to draw in as much fresh air. And then the MAP sensor, of course, is your big player in there. I don't know the exact formula, but that's what it is. It's a mathematical formula. We're putting all this stuff together, and we're going to measure the air by weight, and then we'll inject fuel by weight to match that air so we're at our desired air-fuel ratio. Air-fuel ratios are listed as, well, let's say stoichiometric is 14.7 to 1. That's 14.7 parts of air to 1 part of fuel. Now, how are we measuring that 14.7 parts of air? Everything I've circled up here is how they're measuring. We get this mathematical calculation. This is what this engine breathes. This is how it breathes. We'll put all that together and measure it. It's a calculated airflow measurement, and then we'll inject a certain amount of fuel to match it. So it is a big player, this MAP sensor. Something else it's used for would be as a barometric pressure, so an atmospheric pressure sensor. Atmospheric pressure is important in this calculation too, because if you're driving at sea level compared to driving at 10,000 feet of elevation, there is a lot less atmospheric pressure at 10,000 feet. If there's less atmospheric pressure, then there is less airflow that's going to occur, and so we need to adjust our fuel curve to compensate for that. So what you want to remember for this part is the higher the altitude that you go, the less fuel that you're going to need. The higher the altitude, the less fuel. There's less atmospheric pressure, so the engine does not breathe the same way at higher elevations, just like we don't. So if you think about this sensor being used as a BARO sensor, there are only 2 times that we can use the MAP as a BARO, and you want to remember these 2 times. The first one would be key on, engine off. As soon as you turn the key on, if you look at our generic picture up here to the right, the moment you turn the key on for an engine computer system, it does multiple things. You know, turns the check engine light on, runs the fuel pump for a few seconds, looks at some critical inputs, looks at throttle angle, make sure you don't want to clear flood. It looks at ECT to see where we're at. It looks at the MAP sensor for atmospheric pressure. Because when you first turn the key on, the engine's not running. So what's inside of the manifold? We got atmospheric pressure inside the manifold on initial key on. So the computer doesn't need a separate BARO sensor. We have a MAP sensor that provides that information. Turn the key on, MAP's going to indicate to the computer what barometric pressure or what pressure's in the manifold. And if the car's off, what pressure's in the manifold? We have atmospheric pressure in the manifold on initial key on, or really all the time. The engine's off. It should not trap vacuum in the intake. If you trap vacuum in the intake, you got some kind of major idle air control problem and a plugged up throttle body. And I actually have a video and a case study on that. It was kind of crazy. It was on an RX 300. I'll have to show you that later, but kind of did some crazy things. It wasn't, they weren't focused or centralized around a MAP and BARO problem, but it was a no start from that. So key on, engine off, turn the key on, computer looks at MAP and writes down a BARO number in its memory. So if you're looking at the scan tool, you might see MAP volts and BARO volts on the scan tool, and they're 2 separate data parameters. You turn the key on, let's say you're dealing with an analog type MAP, and this is pretty typical, key on, engine off, MAP voltage 4.5 volts. Of course, it would depend on the car you're working on. And then you'll also see on the scan tool that they give you a BARO voltage too. And so looking at that, if you didn't know, you would think you have a separate BARO sensor. You don't. Where's that number coming from for the BARO? From the MAP directly. Then you start the car, and this one's going to drop to around 1 to 1.5 volts at idle. This one stays stationary. That one doesn't move. So you're driving your car, your BARO numbers, whatever. What you guys need to understand is the computer adjusts the entire air-fuel ratio based on this BARO signal. So what happens if you're driving in the plain states and you start climbing the Rockies? Isn't there a necessity for an updated BARO calculation as you're climbing the mountains? And so there is another time where we can use the MAP as a BARO, and that's at wide open throttle. At wide open throttle, there is no vacuum. At wide open throttle, the pressure inside of the manifold is basically atmospheric. Now, we're not talking about a turbo engine here. We're talking about a naturally aspirated engine. And so the computer will update the BARO at wide open throttle. So you guys find yourselves in that situation. You're climbing a mountain. It's not a bad idea to punch to the floor on occasion. Because what are you doing for your car? You're allowing that barometric pressure reading to update, and the computer can more accurately and precisely control the fuel going into that engine. If that wasn't done, what would happen? The higher in elevation you went, the richer it would run. You're issuing the same pulse width type commands for that load, but that air isn't there. Okay, so 2 times, pay attention to this, 2 times a MAP can be used as a BARO, Just key on engine off and wide open throttle. Idle speed would not be a time we could update the BARO, right? Idle speed would be when our vacuum is very hot. You can't calculate BARO at idle speed using a MAP sensor. Some cars will have separate BARO sensors, but in most cases, the BARO reading is done from the MAP.
Which cars are like that?
Have the separate BARO? One that comes to mind would be the Eclipse that we had in here. They use a 7-pin mass airflow sensor, and inside of that mass airflow, you have your hot wire mass airflow signal, you have a intake air temp signal, and a barometric pressure sensor that are all inside of that. I would think that a turbocharged version, if it was a MAP design, a speed density design, I'm thinking of an older Chrysler here, the old 2.5 turbo they used in like the Daytonas and the LeBarons. That was a speed density engine, and they had separate BARO sensors on that. And that would make sense because, you know, you're not going to update that thing at wide open throttle. You're pressurizing the intake above atmospheric, and that wasn't possible. I'm pretty sure those had a separate BARO. It's pretty tough to name you any more than that because it's not common. Most cars you're using the MAP as the BARO. It just wasn't a need for a separate sensor. Okay, we've mentioned this one before. When we talked about EVP sensors, remember I said EVP sensors are EGR valve position sensors, and they're not good indicators of flow, EGR flow. They just show EGR valve position, and flow is assumed by the computer. And so if you have a system like that, which is pretty common today, for example, my 2008 Chrysler Town & Country is a electronic EGR valve, and it has an EVP sensor inside of it. That isn't good enough for OBD2 as far as EGR flow monitoring. Position assumes flow. You can have a plugged up passage and have good valve position, correct? So we need another sensor that's going to be involved in EGR flow. This would be one of them. Our MAP sensor can be used to monitor EGR flow. So this is just a generic picture. And what we're looking at here would be a decel condition. Right here, you see the RPM dropping. So this engine is decelerating. If the engine is decelerating, what type of vacuum levels are in the intake manifold? If we're decelerating, our throttle is closed. And our RPM is high, right? So actually, vacuum is our highest during a decel. So there is no atmospheric pressure. You're talking, you can be as high as 25 inches of vacuum during a decel. Normal vacuum at idle 17 to 21, you can be as high as 25 on a decel. Higher RPM, throttle's closed. That's what causes it. So during that decel event, what we're looking at would be low voltage on the MAP. Low MAP voltage. That would make sense. High voltage with no vacuum and low voltage with high vacuum. That's how the MAP sensor works. And what you're looking at would be right now at this point, the EGR valve is closed. What the computer does, it's an active test the computer's going to do on itself, is it's going to momentarily open the EGR valve. And when it does that create a pressure change in the intake manifold? If I'm opening up the manifold to exhaust gases, which would be, in this case, we're decelerating, so there's not much, right? We could all agree that we really don't have much back pressure during a decel. So, if anything, though, we're opening up that EGR to atmospheric pressure, right? Atmospheric pressure or above, maybe a little bit above. What's that going to do to pressure in the manifold? It's going to increase, right? So, we're going to have a drop in vacuum or an increase in pressure, and we're going to see higher voltage off of the MAP sensor during this event. This is how EGR flow monitoring is done. This is how a system with no EGT sensor, remember we talked about an EGR exhaust gas temperature, which is used to monitor flow. This would be one of the ways that EGR flow can be monitored using an existing sensor. You might be thinking, well, isn't that going to mess up the mixture? And isn't that going to cause a drivability problem? And that's right. No, because we're decelerating. And when we're decelerating, you don't need any fuel at all going into those cylinders. It doesn't matter what the air-fuel ratio is on a decel. In fact, our cars, I showed you when we did throttle position sensors, actually shut the injectors off during a decel. That's one of the things that make the fuel-injected cars so much more efficient than an old-school carbureted design is you were just dumping fuel out of the exhaust on a carbureted engine during a decel. You're decelerating that engine, you're still pulling fuel in. It's not needed. It's not part of the process. The rear wheels are driving the crankshaft during a decel. So it doesn't matter what we do with the mixture, you're not going to feel that. That's where your EGR flow codes are going to come from. The MAP sensor can be used as a flow monitor. And then number 5 on the list would be, of course, spark timing. Spark timing being a factor that, you know, closely follows the fuel map. If you've ever seen a fuel map or a spark map, they're pretty elaborate. And spark timing would be a factor in here too. So main input for engine load, big time factor with fuel delivery, right? This MAP sensor is. If you have any kind of drivability problem or anything like that, you really want to focus on what this MAP sensors do. In particular on a speed density engine. Now there are systems that use, and none of you mentioned it, maybe we have before, there are systems that use both a MAP and a mass airflow. On those systems, the MAP sensor, it's not part of the same process. We could call the MAP sensor here, he's the starting quarterback, and he put a MAP sensor on a mass airflow engine, he went from starting quarterback to punter. Right? The punter, you can have a whole game where you don't even use the punter. You know what I mean? If your offense is clicking, you don't need to punt the whole game. Primarily, though, when you have a MAP sensor on a mass airflow engine, it is used for EGR flow monitoring. That is its primary function when they do that. Ford didn't do that, but GM did. Most of the GMs that have mass airflows also have MAP sensors. It does change things a little bit. Primary function is EGR flow monitoring. In fact, some of the cars, I've seen this, I think Nissan is one, that have mass airflow engines, they actually call it a different name. It's actually a MAP sensor, but they call it something else because its purpose is EGR flow monitoring. I forget what they call it. Some type of pressure sensor. It is a MAP sensor, but it has a different name. They don't call it a MAP. So this is a generic picture of what an older one would look like. Today's cars, what they're generally doing is putting the MAP sensor in the manifold runner and eliminating this hose right here. This hose was a big problem. Today's car might look like is, you know, the manifold comes up here. There would be a rubber grommet that actually bolts right down inside of the intake manifold. So if you're looking for a MAP sensor, you're looking for a 3-wire pressure sensor that's attached to the manifold, or it's attached to the manifold with a hose. The ones with the hoses, they cause all kind of issues. Made lots of money off of older cars with MAP sensors because the hose would deteriorate, the hose would break. Let me give you an example of what a broken hose would be. Is you're talking, this is broken here, and of course you got a vacuum leak, right? That'd be intake side. This is attached to manifold vacuum. So your first thought with a vacuum leak is this car is going to run a little bit lean, but it's not. This is one of 2 vacuum leaks that I can tell you will not make the engine run lean. The second one would be a fuel pressure regulator hose vacuum leak because your fuel pressure is going to jump up by about 10 psi. Kind of counters that vacuum leak that just happened. But this is, let's say this is the primary one, a vacuum leak on a MAP sensor, this engine is going to run extremely rich. And the reason it runs extremely rich, actually let me take that back. This engine runs extremely rich at idle and low speeds, but runs completely normal at wide open throttle. If you think about the MAP sensor and its operation, that would make sense. What do we have as far as vacuum at wide open throttle to this MAP sensor? No vacuum. We got full atmospheric air going to this MAP sensor at wide open throttle, right? So that's what it normally would read. So car runs great at wide open throttle. But at idle, when we should have vacuum going to this MAP sensor, the MAP sensor is still indicating a wide open throttle condition to the computer. And the computer's reaction is to do what? With high voltage or a high load signal from this MAP sensor is going to be to add more fuel. And so this engine's going to be chugging, rough idle, black smoke. The other day we were working on a car in the shop and we had a MAP sensor connector that was unplugged, reading high voltage all the time. That car would not idle, would it? It would not idle. Now that car's got other issues too, but that was a factor with this MAP sensor. So you can have that effect. That's pretty common on a vehicle with a MAP sensor. Pay attention to that hose. Make sure it's good. I had another one, and this is not common, but what would happen if where this hose connects to, which is the manifold, and the port in the manifold was plugged up. This was on a Honda. I was not working on it, but I was helping someone over the phone, and long story short, after getting 2 MAP sensors and I'm not sure what else they did to it. I told him, based on the map readings he was giving me, and we had a map code on this engine, I told him to check his vacuum supply to the map sensor, and there wasn't any. And if there was, it was very, very small. So checking that supply voltage, checking the supply vacuum is also an important step when you're dealing with maps. I had one, it was really weird. It was a Ford Mustang. Student put an intake manifold on an older design Mustang, non-mass airflow, so speed density engine. And what they did when they bolted the manifold back on is it actually kinked this hose. And so the visual there would be a kinked hose to the map sensor. The symptoms of this car were really weird, because what it would do is it would start up normally, no problem at all. But when you stepped into the throttle, it would hesitate big time. And that part makes sense if you think about it. You start the car, it starts fine, but when you snap it, we get these sudden fluctuations in manifold pressure, right? On a snap, we got a rise in pressure and then a drop in pressure. Is that going to react up here the same rate, or is it going to be delayed? It's going to be delayed. So let's say we're at idle and our map voltage, and this was a Ford, so it used frequency, but so I won't throw the numbers in there. I don't want to confuse you. Let's say the map sensor is reading normal engine vacuum, right, at idle. When you snap the throttle, or when you do a sudden acceleration, that vacuum is trapped in that upper chamber area. And so you have more load than what the map sensor is indicating. So what's the computer not do? We don't have enough fuel, so do you understand why the car hesitates really bad? And then if you held the throttle there, it actually smoothed out after that. And that makes sense too, because any trapped vacuum up in here would kind of bleed out, right? Then we'd have the right pressure indication to the map. Now here's the weird part. Take this same scenario, and you're at idle, and you started the car, it's running fine. You punch it to the floor. The car would really severely hesitate, and then you had to let off because the car really wasn't moving very well. And as soon as you let off the fuel, the car would stall, and it would not restart. You could crank it all day long, and that car will not restart. Here's what happened and why. We have trapped vacuum up here, right? So let's say that we're at idle and normal idle 17 to 21. Let's say we snapped the throttle, we went to wide open, and let's say we still had 15 inches of vacuum still trapped up in here at wide open throttle. When does the BARO get updated? Key on engine off and wide open throttle. So now we just updated the BARO calculation to basically Mount Everest atmospheric pressure, 35,000 feet of elevation. How much pressure's up there?
None.
None. So how much fuel are you getting? None. So when you let off the throttle, come back to an idle, the car won't run. You crank it over, keep cranking it, it's still basing the entire fuel curve off of that 35,000 feet of elevation. How do we reset it? If we shut the key, this is the weird part about this one. If you shut the key off and you waited 5 seconds, it would fire right back up. Because when does the computer update the BARO? Key on engine off, wide open throttle. Now let me restate that. It would be initial key on engine off, wouldn't it? Yes. It's not gonna, if the car stalls, that would be key on engine off, wouldn't it? Yes. But it already has that number written into a volatile memory that it's just gonna keep it till the next key cycle. So as soon as you turn the key off, that trapped vacuum isn't there anymore. Turn the key back on, now we re-update the BARO. All right, so I share that story because I've seen bad map sensors react that way. If a map sensor is failing and does not update properly, can we get weird stuff like that? Recalculations of barometric pressure, the wrong air-fuel ratios, and yeah, you can. In fact, the early Chryslers, one of the things that was part of their manufacturer diagnostic process is if the car doesn't start, was to unplug the map sensor. And why would they do that? Because if you unplug the map sensor, the computer now will not use the map sensor. And it goes into a default mode, and if the car now starts, you have a map sensor problem. Are you going to see a kinked vacuum hose to a map sensor? Probably not. What I'm describing to you only happened to me once in 20 years. But have I seen map sensors that are failing act like this? And the answer is yes. So pay attention to them. So here's what we want to remember as we continue, that map sensors can be analog or digital. This will be the signal. An analog signal, again, to review, would be something like this. And a digital signal would be something like this. And so higher frequency and lower frequency. So this would be an increase in the analog signal. This would be an increase in the digital signal, just more square waves occurring per second. Ford is the only one that used the digital map. Every other map sensor that I've seen was analog. So manifold pressure changes cause map signal changes. So high vacuum would be a low voltage or frequency, and low vacuum would be a high voltage or frequency. And so we can put those two together in our mind. It doesn't matter what type we're working on, that signal voltage is going to rise, or that signal frequency is going to rise with engine load. Page 5, let's talk about the analog map. This analog map sensor circuit, this is just a generic picture, and you should see some familiarities in here right now. And if you're looking at this and you're looking at this part of the circuit, what does that look like? It looks identical to a potentiometer circuit, doesn't it? Guess what? Testing these electrically is exactly the same. You see what the cool part about when we do pressure sensors is when we work on them and we remember all the detail we did, signal fixed high, signal fixed low, it could be this, it could be this. Guess what? It's all the same. And as we continue through this, I'm going to say in here, detailed testing of the map sensor refer to potentiometers. Some of today's wiring diagrams, what they will do on the diagram is they will actually draw this circuit, and you've seen one already. When we did our 5-volt reference circuit, remember the description of the 5-volt reference and all the sensors that were shared. And I pulled that wiring diagram up at the end, and I showed it on what the factory diagram looked like. Actually, it was a Mitchell diagram and the way they redraw them. The drawings of the pressure sensor, the MAP sensor, looked identical to the TPS on the wiring diagram. They drew it like this. Now, why would they do that? That's not how it works. It doesn't have a movable wiper or pointer inside that moves from pressure. That's not what's inside of that, but guess what? That's how it works. So we can think of it like that. And so really, from that point, all this stuff in here doesn't matter. Let me show you the inside of one of these for a second. All right, here's a picture. You got to forgive me if I'm wrong here on this. This might not actually be the inside of a map, but I think it is. Look at all the components in here. There's no way that I would be able to, like a potentiometer, and take the circuit and explain to you that 5 volts comes through a resistor and on its way out, we're 5 up here and 0 here. You put a wiper on here, and that wiper is going to contact the resistor, and any point on the resistor have a voltage reading, send that to the computer. That's pretty easy, right? As you see in the picture, can't do that. So do you understand what that we can think of this circuit as what I drew here in red? It really does us no good to go through this. Let me show you the inside of a mass airflow sensor, and then we're going to do the same thing. We're not going to go through it. Look at the inside of this mass airflow sensor. You think I'm going to walk you through the internal components of this and how it actually works? You're crazy. You see this little chip in the middle right here with all the little legs going to it? Where'd that come from? Who made that chip? Aliens made that chip. It came from the Allspark. Transformers. I'm just saying, I'm not an electronic guy, and I can't walk you through this part. And so if we go back to our text and we're looking at this picture. It says filtering circuit. What's the filtering circuit? That's that guy. It's got all those things going to it. Yeah, good luck with that. It's a generic picture. Okay, and this picture is showing you a silicon diaphragm, and as the diaphragm flexes, its resistance changes, and when its resistance changes, signal voltage is going to change, and that's what's going on inside of this design. Changing pressure up here, fixed pressure here. They call that absolute zero. What's absolute zero? When you guys had air conditioning, you learned that is a complete absence of atmospheric pressure. We have gauge pressure, and then we have absolute pressure. So when our gauge reads 0, is it truly 0? Or is it gauge 0? It's gauge 0, right? And 0 to us is what we're around right now. No pressure, but that's false, isn't it? We know that at sea level we have around 15 inches of, it's not exactly 14.7. It's like 15.1 or 15.2 pounds per square inch of atmospheric pressure. All right, so don't sweat the internals of this thing. What we're going to think of is testing it exactly like a potentiometer. We've got a steady 5-volt ref, got a signal, and we have a ground. Another name again for a sensor ground, signal return. And I'm giving you some voltage readings on here, what you're looking for, common voltage readings. As with other sensors, our range is 0 to 5 volts. But do we want to see 0 or 5 on any sensor that uses a 5-volt ref? No, you see 5, you got an open, right? You see 0, you got a short. Although on some designs we can have 0 and have an open too, correct? Depends on that internal resistor we talked about. That's a good question. If it was over 5, you have a computer problem. And few and far between that you'll have that. Because if it's over 5, what you're talking about is a internal computer regulator problem. And if that's the case, your first thought would be grounds. And if the grounds are not an issue, then it's a computer. I had one that was like 8 volts. I had another one that the 5-volt reference, when you put it on a scope, it should be a steady 5, but it actually looked like this. So that's a computer problem. And would that mess up a sensor's range? Absolutely, but here's the thing. The car probably doesn't start because that not only messes up all of the sensors, but remember, everything inside the computer uses that 5-volt reference circuit to communicate. And so that computer is dead. It's got no injector pulse, it's got no spark. You can't communicate with it. What we're looking for is we want to be somewhere between 0 and 5. And I'm just giving you an example that any sensor that uses a 5-volt reference, you don't want to see 0 or 5. We want to be somewhere in between. And our normal range, I think the key, these are good questions. I think the key to anything when we do diagnosis in this field is to be able to have a checklist in your mind of quick checks that you can do on every car, that you're scanning different things. And one of the quick checks, let me give you a couple. Turn the key on, engine's cold, look at ECT and IAT. They should be what? Should be the same. Car's been sitting overnight. You have the scan tool connected to the car. You're doing a drivability issue on an unknown vehicle. You've never worked on it before, but it doesn't matter. These are some fundamentals you want to adopt. Look at ECT and IAT on the scanner. They look good. What would be the next thing? You haven't even started the car yet. Look at your throttle position sensor. Make sure you're under a volt. Why are we using that under a volt number? That's what all of the cars operate at. Under a volt at idle, and it should increase as we open and close the throttle. So can we do some quick tests on the TPS on any car on the road? Now, you don't know the exact spec, but can we look at ballpark numbers? And the answer is yes. When it comes to a MAP sensor, you need to understand that the MAP sensor, unlike the TPS, that's going to indicate closed throttle, the MAP sensor is actually going to indicate wide open throttle on initial key on. Because wide open throttle, there's no vacuum. And key on engine off, there's no vacuum. So when you look at a map, you're going to see maybe 4.5 volts, initial key on. Then what happens when you start the car? What should happen? It should drop. So is this a preliminary test we can use on any car on the road? Now, you're looking at the map, you understand how it operates, and you know when you start that car that map voltage should drop. Okay? So you have a car with a map sensor trouble code, and you start the car and it stays high voltage. It's an indication of a problem on that circuit. And you pick that up from the driver's seat, sitting there looking at scan tool because you know fundamentals. What should this thing do? How should it react? We want to see this thing drop, and then engine's idling generally between 1 and 1.5 volts. So these are some ballpark numbers I'm writing down for you guys. I have 0.5 volt to 1.5. Some cars will be lower than 1, but between 1 and 1.5 is what I typically see, 1.2 volts at idle. And then what do? Looking at scan tool, when you snap the throttle, what should happen to the map every time you snap the throttle? Map voltage should rise on a snap. But if you're using scan data, you got to remember a scan data process, that update speed can be slow. And if you want to see that, it's a little difficult sometimes. If you want to check both extreme ranges of the MAP sensor, which would be idle and wide open throttle, right? Idle would be the low extreme, and then wide open throttle would be the high end. We want to check both, right? Just like a TPS, you want to check it at idle, check it at wide open throttle, do a sweep test. How do you do that on a map? We don't need to snap it to the floor and hold it at wide open throttle and throw a connecting rod through the oil pan. What do? Turn the engine off. Turn the key back on. What's your map voltage? Same as it's going to be at wide open throttle. So again, this is a fundamental that you'll develop once you understand how it operates, what it should be doing, then you can do those kind of tests. So within 30 seconds, I've looked at ECT, IAT, TPS, and MAP, and I'm saying check, 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 good, moving on. Does that make sense? That's what you need to be able to do. Eventually, you'll be able to. All that information's up there somewhere. It's all spaghetti right now. I'm just giving you some insight on what I'm doing on these cars. So that's why I'm throwing these numbers at you. Not necessarily something that you need to remember immediately, but they're there and you need to understand how it should operate. And we have to be careful doing this. And you're so used to key on, engine off, seeing something like this, and then you work on this Honda, this example, 2007 Honda Civic, and I'm reading 2.8 volts. 2.8 volts on a domestic for us, GM, Chrysler. Ford used the frequency, so not Ford, but 2.8 volts key on, engine off, that's bad. You don't ever want to see voltage that low. But you're working on this Honda, and this is the way it's designed. This Honda was actually designed to be lower because they can actually turbocharge or supercharge the engine and still use the map sense. So check out the NA. This is an NA engine, naturally aspirated, and look at the turbo engine. Same numbers at idle, same number at wide open throttle, but look at the key on, engine off reading. That's totally different, isn't it? I remember my first turbo motor looking at, it was, again, that Chrysler 2.2, 2.5 used in the Daytonas, LeBarons, and seeing 2.5 volts with the key on and thinking I had a map sensor problem. I was used to looking at 4.5. And this is designed this way. Here's why. What you need to understand is that a turbocharged engine will have pressures in the manifold that are above atmospheric. If you're putting pressure in the manifold above atmospheric, we need to measure it so we can add the fuel properly. So we put a different style map sensor in there, one that's calibrated for a turbo, and then also, not just that, we also have to calibrate the engine computer to read that properly, right? That 2.5 volts on a turbo computer means atmospheric pressure, where 2.5 volts on a naturally aspirated computer would be maybe 30,000 feet of elevation. So the computer program's different too. Sensor's different, computer program's different. Yes?
That's why they don't get like 2-bar, 3-bar map.
Yes. A 2-bar or 3-bar map was your comment as far as upgrading. And the equivalent was 1 bar is, I believe, 15 PSI. So a 1-bar map would probably be this factory one, although I don't know if they would classify this as a 2-bar. It might actually be from the factory at 2-bar because atmospheric pressure it's already able to read. So a 1-bar would be your regular map, but look how it's calibrated. At 1 bar, you're going to read 2.8 volts. And this has the ability to read higher. So I believe Hondas from the factory used the 2-bar map, and probably because on those engines they're able to use the same map and not have to alter the map and just change the computer program to read it. Yes.
All right. You're saying this Honda Civic was at 2.8 volts.
Key on, engine off.
And a domestic car is at 4.5 volts?
Yeah, GM and Chrysler would be around 4.5 volts, but that would be on dependent where you live. If you live in Denver, you're not going to see 4.5 volts. That's at sea level. See, I wrote here. That number is going to change depending on where you live. You might see if you lived in Denver, key on, engine off, you might be used to looking at 3.7 volts on a map because you're at a higher altitude.
And if you were to come here to Pittsburgh, you would see like a 4.5.
Yeah,
be different.
Yeah, because we're only about 600 feet of elevation. 1,000 feet on average in our entire area is the highest you're gonna go.
What would that mean for, like, what would it be at a European car, like for them over there?
Oh, it's all in where your altitude is.
Oh, okay.
It's not where you live, it's how high you live. All right, so the turbo engine is going to be calibrated differently than an NA engine. One more piece here, guys, and then I'll let you take a break. I want to jump you down to the digital map, and this isn't anything different. Again, if you look at this much of the circuit, what's it look like? It looks like a potentiometer, right? Can we test this thing electrically the same way? We can, except there's one difference. The signal circuit is a square wave, and it's a big difference. My first experience with a Ford MAP sensor is I replaced the sensor with thinking it was bad, and it wasn't bad. Here's what it was. Older Ford van, no data stream, manual codes only. And here's what I saw in this Ford. I connected to the signal wire of this Ford, and I read 2.5 volts, key on, engine off. So right away, I don't like my number. I'm used to looking at 4.5. And so then I start the truck, and it stayed at 2.5. So my same number was at key on, engine off, and the same number was at idle. So the two extremes, it stayed 2.5 volts. Then I snapped the throttle a couple times. No change, stayed at 2.5 volts. So check my 5 volt reference next, and it was good. Check my ground, and it was like 0.02. So that was good. And so what did I do? I put a MAP sensor in. That, in my mind, that explained why this van had a hesitation problem. Put the new MAP sensor in, it read the exact same thing as the old. What am I doing wrong? It's a digital signal, and what we talked about previously, I believe we did in section 1 under our basic voltage review, is when you're reading voltage that is an on-off 50% duty cycle, that means it's high, the same amount of percentage that it's low, and it's a 0 to 5 volt square wave that's occurring at 90 to 160 times per second. What are you going to read? Average, which is 2.5 volts. And so you have to remember that when it comes to Ford MAP sensors, that you cannot use a voltmeter to measure the signal of a Ford MAP. You have to switch your scale to a frequency scale, HZ, on your multimeter, and then you'll see this kind of number right here. So I'm giving you a number, 92 to 112 at idle, key on, engine off, wide open throttle, around 160 hertz at sea level. We're about 156 here in Pittsburgh, roughly 160 at sea level, and 152 to 156, 152 to 158, somewhere in that range will be here for our altitude. So Ford, everything else is the same, right? How it's used, how it's monitored, barometric pressure, key on, engine off, wide open throttle, 5 volt reference, ground, same checks, same checks. The difference is the signal circuit. And this is more of section 2, which is switch inputs, and I would call this a pull-up design switch input on this particular MAP sensor and its design. Okay, let's take a break there. When you guys come back from break, we're going to talk about MAP problem.